So we have our expression for Newton's third law in terms of action-reaction pairs on two separate objects. And I want to go through a simple example where we would use more or less everything in the textbook about solving interacting objects. And so the example that I want to do is just a person pushing a crate. It's a simple enough example, but it's got enough to it to where we can introduce these interacting object diagrams, and we can talk about the action-reaction pairs. So we got a block of mass M, big crate, right? And then we got person. Closer. Person pushing on the crate. They should be on the ground. Anyway, that looks a little bit better. That's why I stopped drawing stick figures. What does this situation look like if it's on a rough surface and the block is moving at least to the right? Okay, so the first thing that the book suggests is to identify the objects and all the objects that are present, and then to draw what we call an interacting object diagram. So first of all, what are all the objects present in this scenario? The first one is P for person. Okay. And the next one is obviously C for crate. The other two ones that the book tells you to include are S for the surface, and then double E for entire Earth. The entire Earth is present in this example by its very gravity force. And so those are the four objects that are in the system, those are the four objects that are present. The next topic, it seems kind of simple, is to decide which ones are in the system and which ones are in the environment. The environment are forces that usually the surface and the Earth by default are in the environment. And the objects for which the acceleration we're trying to analyze, the motion we're trying to analyze, we include those in the system. So we'll say that P and C are in the system. The surface of the Earth are in the environment. And so what's an interacting object diagram? It represents the objects as circles and places the circles relatively close to each other in the sense of the problem. So let's draw this. These are fun to draw, I think. So we'll draw P with the circle, and then next to it we draw C with the circle. Represents the person in the crate. And since this is a system, well, I don't want to mix steps, but we draw the surface directly below it. I'm going to need a little bit. That should be enough room. Okay, and then we have the surface below it. And below that, we have the entire Earth. So double E. Okay, so this is more or less how we draw these ones. I mean, you look at some examples in the textbook, practice some of them, you'll get comfortable with this. Now, why we draw it like this? Because every force that we see is part of an action-reaction pair. The person pushes the block, the person pushes the crate, right? Well, last time you've pushed something across the ground, the crate pushes back on you. That's just the basics. And so that's represented by the fact that there's an action-reaction pair between those two objects is represented by a line. That's it. And you should label the line. The book suggests that you label the line. I'm just going to label it generic F for force between person on the crate and crate on the person. So every time you see a force, you have to draw a line from the objects that are exerting the force. And so look at the crate. All right, the squigglies on this line mean that it's a rough surface, so it's got a friction coefficient. This is a more qualitative example, so we're not dealing with the numbers, but so the surface actually would have two lines connecting it to the crate. It's going to have a line for the normal force, maybe, yeah, N sub C, and it'll also have a line for the friction force, kinetic friction force. Along with that, so we don't worry about in this case, we're not really concerned with the force of the surface on the, or force of the crate on the surface, because the surface really isn't moving. Now, if we were doing this example on a platform, then it would be a little bit harder, because as we'll see here in a minute, oh, by the way, there's also gravity, right? I mean, the book kind of does something like this. The shape of the object doesn't really matter, or the shape of the line doesn't matter. Obviously, that's G. And then what about the person? The person also has two forces with the surface. It has a normal force, and you might want to even capitalize that to distinguish it between the other normal force, because you'll find in this chapter there's a lot of different objects, and each one of them tends to have a different normal force. Like if you imagine, this pretty simple example of a third law problem might be, you got 3 blocks all on a surface and you're pushing one. Well, all of them have different normal forces because they're different sizes, and so yeah, different normal forces. So cap N is what we'll use for the person, but there's also a tricky one. There's a static friction force, which is kind of a review of how you walk. It sounds silly, but when you walk, you're pushing backwards on the surface, and the surface is propelling you forward. Right? That's why if you try to push back on a slippery, icy pavement, you might fall forward. And if you're like if you're at your desk and you push backwards on your desk, well, if you have like a rolling chair, well, the desk has too much friction, and so the desk will actually be pushing you backwards. So friction force is responsible for propulsion in human walking, obviously, and also in propelling cars. So this person has two forces from the surface, and then it also has gravity. That'd be F sub G as well. So, and then the last step, this looks a little confusing, but in the last step, we want to separate the system from the environment. Draw a box around the, what? I could be wrong, but it looks kind of cluttered with the same weighting. So why don't I draw it on a bigger, thicker weighting? Take advantage of as many of these tools as we can. That's why and this is the system. SYS. Yeah, that actually looks pretty good because that emphasizes the system. So this is a good example of an interacting object diagram. What's the point of it? Well, the point of it is just for us to recognize those interacting forces. Perhaps we can do a more difficult example in a minute, but once we've got the interacting object diagram, we have our template to draw the free body diagram. You know, each one of these objects in the system has its own free body diagram. So let's draw those. You want to draw the free body diagrams in relative proximity to each other, in the same way that you would see, for instance, the particles in the diagram or in the picture. And start with the one that makes the most sense to start with. I think the crate is the easier one to start with. So let's look at the crate. We've got the gravity. So call that, you have to be very careful with your notation, m sub c times g, and then an upward normal force, which in this case is the same. So that's n sub c. And then, okay, so what about the force in the x direction? Well, this is, you would draw the force. I mean, the thing we probably had expected from the very beginning, the first thing that came to mind probably was the force of the person on the crate. And so I'm not going to write the word on. I'm just going to write F of the person on the crate. That activates Newton's third law because we've got a force of one object on another and each of those free body diagrams. And so how the book suggests to do it is to draw a nice dotted line from the force that you just drew all the way to the other one, and then invoke Newton's third law. So this is the force of the crate on the person, which, you know, in parentheses is equal to minus the force of the person on the crate. Okay, and so you're not quite done with the crate. You know to include friction and backwards F sub k. Is it accelerating or not? It'll depend on the problem. In this example, I mean, sometimes you're pushing backwards. You usually push these things at a constant speed. So whether or not it's accelerating or not, that'll just depend on the problem. But, you know, just the point was to identify the action-reaction pairs. Going to the person, got the same thing. We got m sub p times g, and then a bigger normal force. Maybe call it lowercase n sub p. I think I wrote it capital N. Or you could write, I think more standard is n, little n with the subscript. And then we have a backwards, or sorry, the force of the static friction force on the surface. So that's a good free body diagram for both the person and the crate. There's the interacting object diagram. There is the free body diagrams. In this example, I'm not really emphasizing much about summing the forces. Yeah. Okay. So if that's pretty clear, let's try another example where these interacting objects might be a little bit less obvious. Yeah, and the example that I'm thinking of is, this drawing is not going to be great, but, well, it can be. Got the pickup truck. Is that right? Roughly? And the bed of the pickup truck, right? Okay. Yeah, close enough. So we have a pickup truck that is starting from rest and it's got the box in it. You're moving the ancient china, the fancy, I mean like ancient china, I mean like you're moving a box on the truck and you don't want it to slide backwards. So you have to accelerate at a rate so that the box doesn't slip. What's the interaction here? Well, once again, in this case, what's the diagram look like now? It's a little bit different than the person pushing the crate, the truck towing the box. Well, we've got our truck, T, obviously, the block B or something, or the crate, or the, yeah, box, B. We got the surface and the earth. So how would you arrange them? You know, it'd be something like the interacting object diagram would be something like this. It'd be like the truck would kind of frame it, and then below it you have the surface, and then the entire earth below that. And then maybe off to the side some here you'd have the box. All right, so you're just trying to draw the circles in proportion with one another. So what does this diagram look like? Well, we know that the earth obviously, oh, I didn't circle the earth. So the earth exerts gravity on the truck and on the box. Something like that. Surface, right? Surface does two things, right? Surface has a normal force on the truck. What else does it have? Well, it technically has like some sort of friction. You want to call it rolling friction, or you want to call it static friction, it's fine. But what about the box in the truck? So the box has a gravity force from the earth, but it doesn't have a normal force from the surface. It's got it's got a normal force from the truck. So you got two ends here, which again, you might want to capitalize this one. But really the whole point of this example is that what is the force, if they're both accelerating, what's the force making the box not slide? That would be static friction force. So that's another example of an interacting object diagram that might not be as obvious. I mean, anything in the bed of a truck moves along with the truck because there's no static friction. Or sorry, because of static friction, precisely because of static friction. If there was no friction between the box and the truck, what would happen? The truck would accelerate. As the truck accelerated, the person in the bed of the person in the truck would see the box go like this, move backwards, something like this. And the person would see the box accelerate backwards at that same spot. But what would the person on the side of the road see without friction? Well, that they'd see the truck accelerate forward and the box would stay exactly where it's at. These types of differentiating between reference frames. All right, that's another example. The book has plenty of practice examples with interacting object diagrams, and that is helpful. Ultimately, though, we want to end up drawing free body diagrams. And so we'll do that in the next discussion.